In Chapter 8, Part 2, Ionic and Covalent Bonds, we're going to start to think about what happens when two elements come together to create a bond. First, we're going to talk about ionic bonds. So an ionic compound is composed of an ionic bond. So ionic compounds are a metal, nonmetal compound. And we have seen so many of these through this semester. So sodium chloride is an ionic compound. We could have magnesium oxide would be one. We could also have magnesium fluoride. So anything where we have something from the left side of the periodic table interacting with something from the right side. So we know if we want to create sodium chloride, we would have sodium solid plus 1/2 of a mole of chlorine gas, and that would give us sodium chloride. And the delta H on this reaction, or the heat of formation, is negative 410.9 kilojoules. So in this case, we have these two. And so as we're going to start to think about is, can we think about this in terms of a reaction? Can we draw structures? So sodium has a single electron. Chlorine has 7. And so we could imagine a way where the sodium electron is going to be given to the chlorine, to where we're going to end up with sodium plus chlorine minus, where chlorine has all of its electrons. And sodium gave its up. So we know that sodium regularly and easily gives up its electron. It has a low I1, meaning, it gives up an electron. So it's going to easily give up an electron, and chlorine has a high electron affinity, and so it readily takes one. So in this case, when we think about this, sodium readily wants to give up its electron, and chlorine is going to easily accept it. This is a perfect match where sodium will give up its electron and give it to chlorine. And so when we think about this reaction, it's highly exothermic, which means it's kind of going to give off a lot of energy. And we know that we know that solid salt exists. So how are we forming these ionic substances in these cases? So the stability of ionic solids is stable due to the charge-charge interaction. So ionic solids, such as table salt, are stable due to the positive and negative charge interactions. So we know that in this case, when sodium plus interacts with chlorine minus, these two elements are close together and both have a charge. So once we know this, we can start to think about the stabilization. So these are stabilized by something called lattice energy. So lattice energy is the ability for the ions to stabilize one another. So if we were to imagine a sodium plus and a chlorine minus in an interacting pattern, so we'll draw these as circles, and that's going to be terribly looking. So instead we will just have, plus, minus, plus, minus, plus, minus. And this pattern repeats in 3 dimensions. And so when we start to really think about that, it tells us that as we go back in 3D space, we will see all of these interactions. So a lattice of charges stabilizes them. So back in chapter 4, we talked about how a dipole moment could be formed in water to where the water molecules will be surrounded by the ions and vice versa. This is very similar to that, where every negative charge, every negative charge is surrounded by positive charge. So they're stabilizing one another. So every negative charge is surrounded by positive charges. Every positive charge is surrounded by negative charges. So in this case, the lattice energy which will be delta H lattice, for sodium chloride is positive 788 kilojoules per mole. So this is very stable. So when we can start to think about all of these different things, the lattice energy for different compounds is going to change based on the elements. So lattice energy depends on the distance between elements. So lattice energy is derived from the electrostatic. So E sub EL equals K Q1 Q2 over D. So this tells us that the lattice energy is derived from the charge, which is Q, and the space apart, which is the atomic radius, which you can calculate in D, which tells you that a bigger element has a wider distance, so it's going to actually have a smaller electrostatics. So we can start to look at different things and be able to determine what the lattice energy is or predict relative instances between the two. So it's important as we think about ionic bonds to really be able to think about what the electron configuration could be for S and P block elements. So for S and P block, we know that for sodium, we have 1s2, 2s2, 2p6, 3s1. We know that we also see sodium plus, which is 1s2, 2s2, 2p6. This has octet. If you remember back to the ionization energy, we know that the ionization energy increases drastically when we start to take apart core electrons. So sodium 2 plus, which will be 1s2, 2s2, 2p5, means you've removed another electron. This is almost never observed. So what we're starting to see is that the octet arrangement is the moment in which the ion achieves the noble gas configuration, which basically means it has a full octet of electrons. So this is never observed. But let's think about for chlorine. So we have Cl, which is 1s2, 2s2, 2p6, 3s2, 3p5. We do often observe chlorine minus, so 1s2, 2s2, 2p6, 3s2, 3p6. But we also do not observe chlorine 2 minus, where you would add the 3s2, 3p6, 4s1. This is not observed. And so the electron configuration has to do with the octet. It also has to do with the lattice energy. So both of these have achieved octet when they become their preferred ion state. So the configuration of these, is going to help us when we start to think about how these elements interact together. But before we can really start making bonds, let's think about covalent bonds. So a covalent bond is found in a nonmetal. This is in a nonmetal compound. So we have carbon oxygen, you could have carbon hydrogen, nitrogen. Basically anything that we see on the right side of the periodic table interacting with something else on the right side of the periodic table. A covalent bond is different than an ionic bond because a covalent bond equally shares electrons. So when we think about a covalent bond, it's going to equally share the electrons. The electrons act as glue. So we're going to stick element A plus element B, and what we'd like to see is A and B interacting with one another where we have shared electrons. So it is worth noting that an ionic bond does not share electrons. In fact, they do not share at all. But a covalent bond, we're going to have shared electrons. So when we think about a covalent bond, so if we were to have a hydrogen plus another hydrogen, we could imagine that these two electrons come together and fit to create hydrogen. In this case, where both elements share the electrons. So it's also worth noting in this case that two electrons make a bond. And we will see later that sometimes more than two electrons will make a bond, but most of the time just two. So in this case, both elements share the electron, giving both octet. Now, the octet for hydrogen is in fact only 2 because it only has the 1s orbital. But when these two come together, they're creating a single element. And so what we see is that the hydrogen-hydrogen complex, so sometimes we draw the two electrons as a line, would basically have an equal, so the electron density is symmetric. And symmetric is important because in some of the upcoming sections, we'll start to talk about when it's uneven. So it's important to know when it's even and when it's uneven. So let's look at chlorine. So if we want to make Cl2, where we have chlorine with its electrons, so it will have 7 valence electrons, plus another chlorine, which also has 7 valence electrons. So we can see that there are 2 electrons that might want to interact together, to where we could get chlorine with its 7 electrons to interact with the other chlorine. So now, when we were to attribute the electrons to either of these, we can see, and I'll draw the other circle in red. Oops. Both chlorines have 8 electrons around them. This allows them to share the electrons between them, and it's going to give them an equivalent bond. So we could draw this also as Cl 1, 2, 3, 4, where these 2 electrons, so 2 electrons have formed a bond. And so the other ones are lone pairs. So we have 2 electrons in a bond, and I will put a bracket around these, and these are lone pairs. And so I always draw them as pairs. There are some scientists who draw them differently. So some scientists will draw them with lines. And this is a big no. So we want to draw our lone pairs as 2 electron dots, and they should be pretty close together. So definitely not this. So as we start to think about molecules and how they fit together, let's think about what that means. So let's draw some Lewis dot structures. So when we set these up, I will always underline the central atom, unless it's just 2 elements, or in rare cases 3. But if they don't have an underline, they connect together in a single linear line. So let's look at HF. So if we draw our Lewis dot structures, the H and the F, we can see that together, likely they could fit together like a puzzle piece, where the hydrogen is connected to the fluorine by a single lone pair. And all of these now both have octet, where hydrogen has 2 electrons and fluorine has 2 electrons. So let's look at H2O, where oxygen is the center. So we're going to again have hydrogen. We're going to have oxygen with its 6 valence electrons. So we can see that these will fit together in this way. We're going to have hydrogen connected to oxygen, and it will look like this. Now, you may have already taken a chemistry class that tells you that this structure is wrong. But right now we're learning how to draw Lewis dot structures. And in this section, we're really just putting them together like a puzzle. Instead of in some of the later sections in chapter 8, we are going to learn how to do this without using a puzzle. But for now, we want to think about them as a puzzle piece. So for ammonia, which is NH3, ammonia is our central atom. We're going to have our 3 hydrogens plus nitrogen, which has a single lone pair. And so the 3 hydrogens could interact together to where nitrogen would interact with 3 hydrogens just like this. And now let's look at methane, which is CH4. So we're going to have our 4 hydrogens plus carbon that has 4 valence electrons. When you put them together, we can see we will get 4 bonds. So all of these that we've looked at here are covalent bonds. We don't really draw ionic bonds this way. So we're really going to start looking at non-metal compounds as we look at this. All of these examples have things called single bonds. So the real question is, what happens if more than 2 electrons hang out between our 2 elements? So multiple bonds. So a bond contains 2 electrons. So sometimes there will be more than 2 electrons between 2 elements. So let's think about, so for an example, that would be an oxygen-hydrogen bond. So there are just 2 electrons in here. But let's think about CO2, where we have carbon plus oxygen. And so when we create this molecule, and we're going to have 2 of these, we could start to draw something that looks like this. And so one thing you'll notice is we have these lonely electrons. Electrons really don't like to be alone. They either prefer to be in a lone pair of 2 or in a bond with 2 electrons. So these lone pair, these single electrons are unfavorable. And so they are unfavorable. Oops, and we forgot this one here. So we have lots of lonely electrons. So maybe we could redraw this as oxygen with its 2 lone pairs. And then both carbon and each oxygen are going to donate another electron to be in the bond. To where now we have 4 electrons between 2 atoms. And so when we do this, we're going to get something called a double bond. where we have oxygen. So these are what we're going to call a double bond. And so in this case, now everyone has octet, because if we go back up here and look at this structure, so I'm going to highlight all of the electrons around oxygen. And we can see that there's only 7. So if we look at the other oxygen, it also only has 7. But let's look at carbon. So carbon has 2, 4, it only has 6 electrons. So none of these have octet. These elements have octet. But if we look at this structure down here, we can see, whoa, wrong marker. If we look at this structure, they're a little lopsided, but oxygen has 2, 4, 6, 8 electrons. And let's look at this. We also see 2, 4, 6, 8 electrons. And if we use carbon, or the green color for that, we can see that carbon is also surrounded by 8 electrons. So in this structure, all elements have octet. And so when we start to draw these structures, octet is going to be really important. So for now, I know it feels like we're like, I don't really know how we'll draw these. And that's okay. We're going to learn to draw these in a manner that makes sense. But I want to show you that there are different types of bonds. And so the last type of bond that we want to look at is something called a triple bond. And one example for that is in nitrogen gas. So N2. In this case, we have nitrogen with 6 electrons between it. 6 electrons between, and a triple bond. And so in this case, all of these elements have octet, to where we see the either nitrogen has 8 electrons, so all have octet. So we've looked at, in this video, 3 different types of bonds. We have a single bond, which an example would be OH, and it is 2 electrons. We have a double bond, and we can see that between oxygen, oxygen, where there are 4 electrons between. Or we can have a triple bond between nitrogen and nitrogen, and there are 6 shared electrons. So all of these bonds we're going to see over and over again in this section.